So if you choose to pursue further studies in chemistry, you'll find out that every rule that you learn, there are many, many, many exceptions to. So we're going to look at a few of the elements today that are exceptions to the rules that we've learned for electron configurations. So we'll talk about two elements in particular, then we'll discuss kind of why they're exceptions to the rule. So what I want you to do is go ahead and write out the electron configuration for copper and chromium. Go ahead and write out the full electron configuration for those real quick. So you can pause the video and do that. Alright, so you should have gotten something similar to this. If you got something that was slightly different than this, either go back and figure out where you went wrong, or if you Googled it, you would have gotten the actual correct answer, and that explains why yours doesn't match what I have right here right now. But let's go ahead and look at the orbital notation for these two elements, but only for the 3d orbital. Okay? So the D sublevel has 5 orbitals. So I'll label that 3d. So let's put in the electrons 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So down here we have 4, 1, 2, 3, 4. Let's go ahead and show the 4s as well. Okay, so for both of these elements, they're full. So it turns out, and you could probably expect, energetically, orbitals prefer to be full. Okay, sublevels prefer to be full. If they can't be full, they like to be empty. Okay, so empty is also a energetically good situation. But another fairly energetically good situation is to have a half-full sublevel. Okay, so in the cases of copper and chromium, the elements do a little bit of shifting in order to make sure that all their sublevels are either full or half full. So in the case of copper, let's write the true electron configuration. This is what is actually observed if you were to be able to look at a copper atom. So you have 1s2, 2s2, 2p6, 3s2, 3p6. So here's where it gets a little strange. 4s1 to 3d10. Okay, so this electron moves into the 3d orbital. So you might be thinking, well, this violates one of the basic rules that we learned. It violates Aufbau's principle here. But the case is the 4s and 3d sublevels are so close in energy that they are almost equal. Okay, so when they're that close in energy, electrons can move from one to the other if it creates a more energetically favored situation. So it turns out this is the true electron configuration for copper. This configuration is far more energetically favored, or far more stable than this configuration. So now every sublevel is full except for 4s1, and it's half full, and half full is still energetically okay. So you can probably guess what's going to happen with chromium. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. So this electron moved over, one of those electrons moved over there. Okay, so now chromium, this is its true electron configuration. Now every sublevel is full except for 4s1 and 3d5, and they are, or 4s and 3d, they are both half full. Okay, so this is a far more energetically favored situation than is here. So in the periodic table, there are many exceptions when you come down to the F block. Okay, a lot of strange things happen down here, but primarily of the elements that we deal with, we want to look at copper and chromium as being the two exceptions, and we'll see that the elements straight below them often have similar situations happen where a s electron moves to a d orbital. Okay, but rather than you having to predict when this is going to happen, I just want you to be familiar with the situation of copper and chromium. You'll see that over and over throughout your chemistry career. So go ahead, when you think about either one of these elements and you think about their electron configuration, you should automatically think, okay, there's probably something strange going on here with these two.